Okay, welcome, Ralph and Jordan, Victor and Bradley and Jesus. Uh, this is another big day. This section is like the section of the entire quarter. We're breaking it up into pieces, and each piece is still a lot. So we do have a lot to talk about. I wanted to remind you a few things. In a little more than a week, what's coming up?
Our first exam.
Your first exam. So I strongly recommend you do the practice proctorial quiz to make sure that it works. So again, it's easy to do. You just pop on in and see if it worked, and if it didn't, then you're done. But otherwise, you should be fine. And probably if it worked last time for you, if you had this, with me or with use Proctorio, then it should still work. But it can't hurt to try. So that's just a note. And then I want to remind you that for some reason, if you don't have a webcam, for example, or can't get your computer working with Proctorio, then the college has computers you can check out for the entire quarter. So, and no charge, which is pretty cool. So that's just a big note, is that this is the time to start thinking about that, making sure that your technology works. So I want to share my screen and then talk about the material today, which is very theoretical. A lot of theorems and definitions. That's what today's about. So the plan today is, as always, we'll start out with Q&A. And Jacob, you said you heard Proctorio. You might have not had the volume on right away. And that is the test. Oh, that's right. Sorry, I made a mistake. There is no Proctorio next week. That's right. This is the first class we're not doing Proctorio. All my other calculus classes and statistics do Proctorio. So yeah, you don't have to worry about that.
Yeah, that's what I was thinking. I was like,
sorry.
wait, Proctorio?
That's right. I forgot. I'm totally off key base. So sorry about that. There is no Proctorio because we're not doing it in this quarter. But you should make sure that your internet's working, because if you can't open the internet, you're not going to be able to open the test and then write it down, take a picture of it, and then pop it onto Canvas. So that you should know how to do, but that shouldn't be a problem. So we're continuing on with this 4.10, which is really, it's not a section, it's a chapter. Just let you know that. Don't treat this as a single section, because it just isn't. I really like the book, the way it writes, the way the author writes stuff, the way the examples go, the theorems, the definitions, the wording is really good. But I hate the chunking. So 4.10 is like, I don't know, 20% of the whole class, just to let you know, even though it's just one section. So I want to give you a big warning about that. And that's why we're spending like an entire week basically just on this 4.10, because it's all the important definitions that we're going to have. So in particular, here's some definitions we're going to be doing. We're going to be talking about the definition of a subspace. So that's more than just a subset. It's a subspace, which means not only do you have a subset, but also if you do linear algebra on it, it doesn't go away. You don't leave it. So we'll talk about it. Then we'll talk about subspaces and the spanning set. So if you have a space, then what does it mean to be a subspace of that space? And how do you find a set of vectors that span that space? So again, we'll get into that. Then we'll talk about how do you define a basis? So yeah, you can get vectors that give you the space, but you don't want to deal with a million vectors. So what's the smallest number of vectors, and what vectors are those, so that you can really work with a space, a vector space. Okay, and then we're going to get into something called the exchange theorem that talks about comparing two spaces, basically. And then after that, we'll talk about the dimension. So for example, the screen you're looking at, what dimension is that? This is an easy question.
Two-dimensional.
Yeah, it's two-dimensional, right? And that you all got in your mind, no issue, right? Okay, whereas our visual universe is how many dimensional?
Three.
Three-dimensional.
Three-dimensional.
Okay, so I'm putting in the things that you already know. You better know that, by the way. But then you want to abstract it. So you want to say, what if you had a 9-dimensional space, and then you had 6 vectors in it? Then what's the vector space of the span of that space? And and that'll be the dimension basically. So we'll talk about that, and we'll show that it's well defined. So the number of vectors you grab is always going to be the same as long as you define it correctly. Then we'll talk about basis, span, and linear independence. So we're going to look at relationships between them. And then we'll get into the existence of a basis. So the idea is, you know, when you learn in whatever 6th grade how to graph a point, okay, you all know how to do that, right? You better. What do you learn at the very beginning?
You learn what X and Y correspond to?
Yeah, so you learn that you walk over to the right by a certain amount, and then you walk up by a certain amount. So in a way, right and up, right 1 and up 1 are the basis for R2. Okay, but it turns out there's lots of bases for R2, but there's always going to be, you're always going to have 2 of them, 2 vectors, but you can choose other vectors, it turns out, and that you don't want to tell 6th grader, by the way, but you're not 6th graders anymore, so you can handle it. So we can talk about that a basis always exists. And not only that, if we start out with a couple vectors, let's say we start out with 2 vectors. Let's say you take the vector from here to Mars, and then you take the vector from here to Jupiter. Okay, and right now they're not collinear, by the way. Then is there another vector you can draw so that you have a basis of the universe, of the visual universe? And the answer is yes. And that's called the extension theorem, is that you can always add to a basis of a subspace to get to a basis of a larger space. And that's this extending a basis theorem. And then just so you're ready for homework, I try to do what's on your homework. I don't know if you realize that. I don't know if you figured that out, but I try to make sure that I go through the book up to where your homework is covered for the homework that's due in a couple days. And there is one problem at the end on taking a matrix and saying what is a kernel of the matrix. There's a whole bunch of other stuff you do with matrices, and that'll be on Wednesday that we'll talk about that. So we'll talk about the kernel of the matrix. It's not a hard definition at all. And it kind of is a relaxing thing after all these other very theoretical things. So that is the plan for today. Hopefully that'll work. And so I'll pop in. Do you have any questions? That could be from homework. It could be from other things. Whatever it might be, I'll be happy to answer any questions you might have.
Yeah, can we go over 31, please?
Okay, so let me go find it. So 31, just a minute. That's a biggie, so we'll get there. Just a second. I'm just curious, when I minimized that, did you see anything happen or not?
Nope, it was just the same screen.
Okay, yeah, see, there's all kinds of stuff going on my screen that you don't even notice. Okay, so 31. Okay, so let's take a look. And here's some vectors in R4, okay? And so the first part's gonna be really easy. And that is, I'm not gonna read off all the vectors. Hopefully you can see the screen, right? You can read this. The vectors can't possibly be linearly independent. Tell why. And this is supposed to be easy. You don't have to do any RREFing or anything. How come?
2 of the rows are identical.
Yeah, but I want to do an easier way without even looking at the rows and columns.
There are more.
Oh, there's free variables, right? Or
yeah, how many vectors are there?
5.
5. Remember we had a theorem. What was that theorem called?
Too many vectors theorem.
Yeah, too many vector theorem. So by the too many vector theorem, I like that. I named it. The book doesn't have a name for it, but I think with this name, then you'll never forget it. Am I right? Too many vectors theorem. In particular, 5 is certainly greater than 4. I think you all know that. the vectors cannot be linearly independent. Is that totally clear so far? Okay. Yeah, you can also, look at the fact that two of the rows are the same, but if they weren't, it still can't be linearly independent. Do you see the issue? Okay. Next, obtain a linearly independent subset of these vectors, which has the same span as these vectors. In other words, find a basis for the span of these vectors. Okay, of course, we haven't defined a basis yet, but that's what we're doing. All right, so for a first thing is we need to somehow get these vectors, right? Okay, and you could look at it and hope you get lucky. The problem is, yes, you notice that there's two of the rows that are the same. That actually is not, we can't get rid of a row because we can only get rid of a column. Does that make sense? A vector. Any questions on that? Is that totally clear? Okay, so what we need to do is we need to get a linearly independent subset of these vectors. So how might we go about that?
Yeah, that's what I found online, was to look at the pivot columns, and then those would be the vectors that would be in your subset. But I mean, I don't really know how to RREF this thing. So
Right, well, first thing, what matrix are we looking at?
the matrix of all the vectors, right?
Yeah, we're looking at the matrix of the vectors, and notice we have A's and B's involved. And you got to live with that, and we can live with it. So we have A's and B's involved. The other thing you can do, and this is just so that you have less writing, and this is something you noticed already, is that the fourth row is meaningless. Do you agree?
Yes.
So we don't have to rewrite the fourth row because that's not going to change anything. So you can get rid of the fourth row, and we're just counting which vectors are needed. So the fourth row is meaningless. And what we need to do is we need to find, so that means that at most you're going to be able to find 3 linearly independent ones, because this is really sitting in R3, because the fourth row is meaningless. Do you all agree? Any questions on that? Because the fourth component of R4 is not doing anything for us. So you can look at this as R3 instead of R4. Okay, and that makes things a little bit easier. And if you want to make a matrix out of it, you can. And so I'm going to do that, but I'm going to get rid of that fourth row. Are you okay with that? Okay, I mean, I could prove that that works if you want, but hopefully you all can kind of see that that should work. So let's go ahead and make a matrix. And I'm going to make it as big as I can and then start adding in. So I need 2 more columns. And 1 more. Okay, so what we got is 1, 3, 1, 2, 1. Then we have B plus 1. And of course, we don't know what B is. It is what it is. Then we have 3B plus 3. Then we have B plus 2. Then we have 2B minus 5. Then we have B plus 2 again. Okay, notice, by the way, actually, I can look at this, and the 5th column is the same as the 3rd column. Do y'all see that? Oh, no, it's not. It's almost
No,
same.
it's not. It's very similar, but
yeah, I was off by 1. Sorry about that. I was trying to save time, but it was wrong. So B plus 2, no, off by 1 little bit, and then 2A plus 2. That's too bad. And then the others are A, 3A, 2A plus 1. And then negative 5A minus 7. Oops. Any questions so far? Okay, it's a big matrix, but we do what we have to do. One of the things to note, by the way, is that there are only 3 rows here. Do you all agree? So at most, we're going to have 3 columns that are linearly independent. Are you good with that? Because you can't have more pivots than number of rows. So that's good enough for that. Any questions so far? Okay, but we can also notice, and I'm going to just do this right away, just by looking. Notice column 2 is a multiple of column 1. Do you see that? So I can actually remember, you can do row operations or column operations. Okay, except you can't switch columns if you're going to be doing RAF, but you'll notice that column 2 has no chance of being one of what we need. Any questions on that? And in particular, if we do the old multiply by b plus 1 and subtract, because that's what we should do, then I guess I should copy and paste so you can see it go. There we go. Let me do it on a new line. This is too big. Then this b plus 1 becomes a 0 because I'm multiplying by b plus 1 and subtracting. This b plus 3 becomes a 0 for the same reason. And this b plus 2 becomes just a 1. And if I multiply by b plus 1 and subtract, then that is a -7. And a 1. Any questions so far? Okay, I can also multiply by a and subtract. First row by a and subtract from the third row. And that guy becomes a 0. The second one also becomes a 0. The third one, if I multiply by a and subtract, I get a plus 1. Make sure I got this right. Yeah, so a plus 1. And then if I multiply by a and subtract on this other one, I get -7a minus 7. And the third, if I multiply by a and subtract, I get a plus 2. Any questions on that? Make sure you watch my mistakes. Make sure I didn't make any. But so far, so good. Okay. Now what can I do? What's your ideas? It's kind of last important step.
Multiply row 2 by -a plus 1. Or
Good. And
-1 times a plus 1.
And add it to row 3.
Yes.
Good. And that's what we want to do. So that becomes a 0, and that's what we want. And the second one also becomes a 0. Do you see that? If I multiply by -a plus 1 and add up. And then if I multiply 1 by -a plus 1 and subtract, I get 1. All right, we now have an REF, which is all we need. We don't need a REF. So what are the pivot columns?
1, 3, and 4.
Yeah, 1, 3, and 4,
5.
exactly. 1, 3, and 5, yeah.
Yeah.
1, 3, and 5. So I'm going to take vector 1, vector 3, and vector 5. And that will be the linearly independent set. So I take getting there, just a second. There we go. So vector 1 is 1, b plus 1, a, and 1. Ah, shoot. Kind of want those on the same line. There we go. Comma. There. Now I'll suggest. And the others were, let's do this. 1b plus 2, 2a plus 1, 1. And then let's see, we don't need a fourth one, we need 3 of them. And the last one is 1b plus 2, 2a plus 2, 1. And that is the collection we wanted. Any questions on that? Did that make sense? Or did I lose you somewhere along the line? Make sense? Okay. There was a question, and this will be the last one I look at, is number 16. Just want to let you know, do you see why I am not going to make you use Proctorio and full computer typed in questions and all that on the exam?
Yeah, because it might take like 4 hours.
Just to do one problem, exactly. So handwriting this is so much easier. Do you agree? Even that this looks beautiful when it's done, but it's, you know, because I have bad handwriting, but so that's why the exam is going to be handwritten. Okay. But in the real world, you want to type everything because you have 4 hours. But the testing isn't real world. Okay. Which means that, by the way, in your presentation, you should be typing everything because that's supposed to be real world like, which isn't for a few months. Okay. So now let's look at 16. So I need to find it. And just a minute. Let's see if this works. Okay, so here's number 16. Are the following vectors linearly independent? If they are, explain why. And if they're not, exhibit one of them as a linear combination of the others. So give a linear independent set of vectors which has the same span as the given vectors. Okay, how do you tell if vectors are linearly independent? What's the easiest way? Especially on a 4x4.
Check if one of the rows is all 0.
In
In the RREF, I mean.
In the RREF, yeah. And actually, all you have to look at when it's square, you can use TFAE. Do you agree? So if they're linearly independent, you better get the identity. Any questions on that?
You can use the determinant too, right?
You can, and that will work. But here's the problem. That will work for answering the first question. But the second question, which is exhibit one is a linear combination of the others, that one's going to be harder. Does that make sense?
Yep.
Okay. Since it's always linear independent if there's a row of zeros, right? When you have the number of rows equals the number of columns, then that's true. And row, when you say it, if there's a row, but not really theirs, it's if RREF of the matrix has a row of zeros. Okay, not like what we're looking at right now, there's no row of zeros, but these turn out to be linearly dependent. So with this one, just go to old-fashioned numbers, which you are allowed to do. What's the easy way of RREFing this guy?
Probably
Well,
with
first
computer.
eliminate the, well, yeah, the computer.
Yeah, use a computer. Got it? Okay, do you agree that that's the easy way? So I can't do this in my head so fast. it would take forever for me. Has anyone else actually, since it's on paper for you, you might be able to look down at your paper if you have it near you. Did you RREF this matrix? And we can put that out. So, okay, so just a minute. Let me create a matrix out of it. Always takes time. So let me go to insert equation. Bracket matrix. 4 by 4. I always forget. I hit the backspace first, then 4 by 4, then 3 by 3, and I add one of each. And then add a column. Okay, so can you, first row, good, that's what I want to see. Wait a minute. You're right in the first row, but you have 5 numbers and there's only 4. I'm a little worried about that. Yeah, don't add the 0 vector. You never want to do that. So 1, 0, 0, negative 6 is what you get. The second row, 0, 1, 0, 4. The third row is 0, 0, 1, 3. And I know the fourth. Am I right? Okay, so immediately we see that this is linearly dependent. So since this is not, in fact, let me write that down since I'm in equation mode. I actually can get to not equal to. This is not equal to the identity, because that's what matters for now. We can say that these are not linearly independent. Or let's say these are linearly dependent. Any questions on that first piece? Okay. So if they are, we don't have to worry. Okay, but if they're not, we need to exhibit one of them as a linear combination of the others. Okay. Any questions on that? Okay. So how do we do that? And first thing, which one can be written as a linear combination of the others?
Or it can be written as a linear combination of the first 3.
Exactly.
Well, the fourth column.
Exactly. And when you do this, when you create the matrix and then REFing it, you're solving for the A, B, C, and a D. Do you see that? So here, we can let D be 1 because that's the free variable is D. Is that clear? So in that case, because of that, what we can say is that A, so let me write A comma B comma C comma D is equal to, well, I'm going to let D be 1. So then A is equal to 6. B is equal to -4. C is -3. And D was 1. That's what we just solved for, isn't it? Any questions on that? Okay, and it's always a good idea to check that works. So for example, the first one, you just need to go 6 minus 4 minus 3 plus 1. It works, you get 0. The second one, 18 minus 16 minus 12 plus 10, and that does work. So you can check the third one too. So that means that 6 times the first plus 4 minus 4 times the second minus 3 times the third plus 1 times the fourth is equal to 0 vector. So that means I can move the first 3 vectors to the right. And I'm gonna just say these are v1, v2, v3, v4. So I don't have to type them all out. And I can say that v4 is equal to, so then if I move everything over, I get negative 6v1, and then plus 4v2, and then plus 3v3, like that. Any questions on that? Okay. And then also give a linearly independent set of vectors which has the same span as the given vectors. And so the last part, that's easy. In other words, since we wrote before as a linear combination of 1, 2, and 3, we just want 1, 2, and 3. So our answer to the last part is that our spanning set that is also linearly independent is just going to be v sub 1, comma v sub 2, comma v sub 3. Sub 3. Have I lost anyone? Because that was a lot of stuff and a lot of language that I know, but you're new to it.
So basically, when you have a pivot, those are independent, linearly independent, right?
Right. So you find the pivots, and then you go back to the columns themselves and write those. You can't just say 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0. That doesn't work. You need to move it back up to V1, V2, and V3. Does that make sense? Okay, any other questions on this? Okay, it's real hard for me to know where you might be confused. One is I can't look at to see, that for most of you, that expression on your face was like, I have no idea what you just said. I'm pretty good at seeing faces, but if I can't, I can never figure out if you're confused from your name on Zoom. So you have to let me know if there's anything that you don't understand. Okay, and not just when I'm doing homework problems, but also during the, talking about new material. Okay. And did we make d equals 1 to make it linearly independent? We made d equals 1. See, d is a free variable, right? Or v4 is a free variable. Free means you can let the symbol to be anything you want. You can get the parameter to be anything you want. So I let the parameter be 1. I could let it be -1 if I want. I could let it be 7 if I want, but 1 is pretty easy. -1's also easy. Does that make sense? So D is a parameter. Okay, any other questions before I move to new material? Okay, let's do new material. And we have a lot of new material, by the way. So there's a lot of definitions and theorems today. So I'm going to go over them, do some examples, go over more, do an example, et cetera, And this is a big one. As I mentioned, this particular section, 4.10, mark that. This is the section, okay, for the course in terms of ideas, okay? We've already talked about matrix arithmetic. All that's important too, and you use it a lot. But in terms of vocabulary, today is the vocabulary day. And another major vocabulary word, we've already had span and linear independence. Those are two biggies. Here comes the next biggest, and that is subspace. And what this definition says is the following. Let V be a subset of Rn. Y'all know what subset means, right? Then V is a subspace of Rn if all three of the following hold. This is not a TFAE. This is all three must hold. One is a zero vector must be in V. So if V doesn't contain the zero vector, forget it. You have no chance, you're not a subspace. So often, if you're ever trying to show something isn't a subspace, that's usually the first thing you look at. It's usually really easy to decide whether zero works. Okay, and number two is V is closed under addition. V1 plus V2 is an element of a V for any V1 and V2 and V. So no matter what two vectors you grab from the vector V space V, if you add those two vectors, you stay in the vector space V, in the subspace V. Got that? And then 3, V is closed under scalar multiplication. Remember, scalars are numbers, real numbers. So in particular, KV is in V for all K in real numbers and V in capital V. So that's a big, big definition. And it gives us major things. And notice, remember the name of this class?
Linear algebra.
Right. Do you know what linear means?
Relating to lines.
Yeah, in particular, lines are equations, right? The equation of a line. Because remember, you're thinking about a line, you're probably thinking geometrically, but that wouldn't be linear algebra, that would be linear geometry, right? So relating to linear things algebraically, and in particular, you're allowed to add and multiply by constants when you're talking about lines, right? And that's what this is. So that's why this fits in with this class real well, because that's what linear is all about. It means that you should be able to add two things and stay in it, and you should be able to multiply by a number and stay in it. And that's what kind of lines are. Any questions on that idea? Now, it turns out not all lines are subspaces of Rn. How come?
Did you say not all lines are in a subspace?
Not all lines are subspaces. So why not?
Because not all lines meet all 3 of these criteria.
Yeah, but what's the easiest?
0, I don't know how to say that sign V.
Yes, is an element of, is how you say
Is
it.
an element of, okay.
Yeah, so in particular, geometrically, the way you think of it is that if a line goes through the origin, then it'll be a subspace. And if a line doesn't go through the origin, it won't be a subspace. Because if you don't go through the origin, you don't contain 0. Any questions on that? Okay, now remember that linear algebra is not really about lines only. It's, you want to jump dimensions. What's the next dimension after line?
Plane.
Yep, a plane. But again, not all planes are subspaces, but all planes that go through the origin are subspaces. Because again, you need to have the 0 is in V. These other two guys tell you have a plane and not some paraboloid or something. Does that make sense? So just geometrically, you can think of it that way, is that the 0 in V tells you it has to go through the origin, and the other two tells you how it has to be flat. So lines are flat, planes are flat. And then you can use your imagination and do 8-dimensional things being whatever mean flat is. And this is what flat means. Any questions on that idea? Okay, so for example, how about y equals x squared? Do you think that is a subspace of R2?
Yes.
So let's look at it. You can always guess and then check. Never hurts to guess. Okay, when I say is y equals x squared, I mean all the points on y equals x squared, a subspace of R2. Well, let's try it. All right, give me a just a point. First thing, is 0 in on this parabola?
Yes.
Yeah, so notice 0, number 1 is good. I'm just gonna write number 1 good. 1 good. Okay, is it okay if I just write that? Everyone sees that the y equals x squared contains the origin? All right. Is it closed under addition? Can you give me a point on a parabola, some general point? Not two horrible numbers, no?
One,
So
one.
let's 1, 1. Good. Those are nice, pretty numbers. Okay. Can you give me another point on the parabola?
2, 4.
2, 4. Okay, this is not a trick question, by the way. And you better all tell me if you add the vector 1, 1 plus 2, 4, what do you get?
3, 5.
3, 5. All right. Is 3, 5 on the parabola y equals x squared?
No.
No. So is not on the parabola. So what can we conclude?
It's not a subspace.
Yeah, therefore, there's not a subspace. Any questions on that? Okay, so a parabola is not a subspace, which is a good thing because this is called linear algebra. And parabolas are about nonlinear as you can imagine, right? That's the whole point of parabolas. It's your first example of something that's not a line when you're learning how to graph stuff, right? So parabolas better not work. Any questions on that? Okay, so that is not a subspace. Okay, I want to give you a note, and this is one of these that put in your mind, but don't release it for like 3 or 4 weeks. And that is, we're gonna have this all in general ideas, and it's still gonna be, I don't have to change anything. Okay, all these definitions are still gonna hold. I've told you before, vectors for you guys right now means bracket with a bunch of numbers with commas in between and end of bracket. But in a few weeks, that's not going to be the case. And all this will still work. So just kind of keep that on hold. But I want to let you know, for later, that all these definitions, word for word, are going to be working in general too. That's one of the nice things. The way I've written the definition, nowhere does it talk about a bunch of numbers. Do you see that? It just has the word vector. So that definition is still going to work later. Okay, any questions on the fact that this is a subspace? Okay, how about this one? Let's let A equal the 2 by 2 matrix. Three, comma 1, whoops, 3, 1, 2, 4. Nice little matrix. And let V be the collection of all vectors V such that AV is equal to 0, which we're going to talk about a little later too. So I figured good time to have an example like it. Is that a subspace? So is this collection a subspace? Of R2. Any questions on the question? Okay, what do we have to do? And the hint is 3 things. What's the first thing we have to do?
Determine if A is an element of 0 isn't included in the element of V.
Right, of this subset. Okay, of V. Right. So is it true? And this is easy. 1 is always easy, by the way. If I take 1 times 0, what do I get? I'm sorry, A times 0, what do you get?
0.
What's A times 0 vector?
0.
Yeah, that's the 0 vector. So that's good. So good. Any questions on number 1? So do you agree, at least so far, that's always easy to show that the 0 works. Okay, let's go to number 2. Okay, well, what do we have to do?
Add a vector and the matrix.
Right, so what we have to do is suppose that AV equals 0 equal AW. With, and now let's, I'm just going to make up some V's and W, and not with numbers, but with letters. With V equal, so now we're talking, these have to be column vectors. This way, nope, do it this way. So V is AB. And just so I don't have to work too much harder, W is CD. So I need to look at A times V plus W. Any questions on that? All right, well, remember we had a theorem about A plus times V plus W. Do you remember what that theorem was? It was a multiplication matrix theorem. It's called the distributive property. Do you remember that property?
Oh, is it like equals AV plus WV? I mean, WA, sorry.
Plus
WA.
AW.
Yeah.
Definitely don't want to go WV. That's the AV plus AW, but what's AV?
0.
Yeah, AV is 0. NAW is?
Also 0.
And what's 0 plus 0?
0.
Yeah, the math is never hard. This is linear algebra. This is not, exponential, logarithmic, quadratics or something. This is all linear, never hard math, but understanding concepts is hard. Do you agree? In this class? And keeping track of negative signs. Okay, that's number 2. That's good. That's what we wanted. Let's do number 3. So now we have AV equal 0. We need to find A times KV. But guess what? We had a theorem about multiplication of matrices when there's a constant. You remember what that theorem says? Yeah, a KV,
AB.
almost KAV. That you can pull the constant out. I don't know if you remember, but that was a theorem. That was one of the properties also of matrices. But KAV is equal to K times 0, and K times 0 is 0. So therefore, V is a subspace. Any questions Any questions at all on these two examples? Okay, I'm not going to have time to give examples of everything I do, but subspaces are so important. I think I better give you examples. You definitely need to decide whether something's a subspace.
What's the difference between subset and subspace?
Okay, so for example, a parabola is a subset of R2, which means every point on the parabola is in R2, is on the plane. Do you agree?
Yes.
But it's not a subspace because it doesn't. So a subspace just means it's contained in it, and a subset means it's contained in it, and a subspace means it's contained in it, and the three properties must hold.
Got it.
Do you see the difference?
Yes.
And they're really important differences. So get these three properties like ingrained in your mind. When I tell you something's important, I really mean it. Okay, we don't have that many things, but they're all happening in this section. Okay, linear independent, span, subspace. We have another couple to do today. Sorry. Okay, just a note. And that is, and you'll hopefully be able to convince yourself, is that it's enough to show that AV1 plus BV2 is in V for all of AB that are real numbers and V1 as capital V. The reason why it's enough to show that is that to show number one, what should I let A and B be?
What was the question?
To show number one, what should I let A and B be?
2.
Yeah, 0.
Yeah, if they're both 0, then that just says zeros in V, and that's what we want, right? To show number two, what should I let A and B be? Pretty easy. Not as easy as the first one, but easy.
1.
Yeah, if I let them both be 1, that's number 2. Do you see that? To show number 3, what should I let A and B be equal to?
1.
No, that would show number 2 if they were both 1. Okay, this is a little harder to think about, but it's actually not bad once I say it. Just let A be K and B be 0. Okay, and that does number 3. So basically, with this thing, you can get all 3 at once, but I do warn you, getting all 3 at once is usually harder than doing them individually. But that's a theorem I basically just proved by saying it, without writing it down. But that's how the proof is. You just set A and B to be the nice things. You'll get it. Any questions on that note? Okay, so here's the theorem. And that is the following. V is a subspace of Rn if and only if there exists a set V1 through Vk in V called S, such that V is a span of S. That's a really important and useful theorem. So one is it says that the span of a set is always a subspace. And the other thing it says is that if you have a subspace, then you can always list some vectors and say the span of those vectors is a subspace, that it's always possible. Okay, so further, if W is a subspace of Rn and V1 through Vk are in W, okay, then V is a subspace of W. So what this says is we were talking about subspaces of Rn, but you can actually talk about a subspace of something smaller. So for example, you can talk about R3, and then you can look at a plane through the origin in R3. Y'all agree that's a subspace of R3? But then on that plane, we can look at a line through the origin that's on that plane, which is so that'll be a subspace of the plane. Anyone lost on what I just said? So that line that's on the plane through the origin is a subspace of the plane, and it's also a subspace of R3. So there's like a chain of sizes. And everything is always a subspace of itself, by the way. Any questions on these subspaces? Okay. Span is pretty easy to go one way. The span is a subspace, and that comes right from the three things. Because remember, the span is a set of all linear combinations. You let all the constants be zero, you get zero. And since it's linear combinations, linear keeps it in there. Adding's good and multiplying by a constant, you stay in. Do you see that? That's kind of the proof there, and vice versa. So I don't have time to prove all the theorems, but I thought I could kind of explain this one. Any questions on this theorem? Okay, so let me move a bit more. Okay, so if V is a subspace of Rn, then there exists linearly independent vectors, S equals V1 through Vk in V, such that the span of S is equal to V. This is very important. Okay, this is a really important theorem. Okay, so it says that whenever you have a subspace, you don't have to list every vector because there's an infinite number of vectors. So for example, for a plane in R3, then you're going to look for linearly independent vectors that give you that plane. Okay, and what you're going to do, by the way, a plane to the origin, by the way, what you'll do is you'll take two vectors on the plane that are not collinear, and that will give you the span of that plane. Any questions on that idea? Any questions? Who's lost? The corollary is more important than the theorem. Okay, so let's do an example. And the idea is, we kind of just did this. And when I say just, I mean today. But what's the very first thing after I went over the agenda that we did?
Determined if the vectors were linearly independent or dependent.
Yeah, and in particular, we did a little more than that with the same idea.
We also found a subset of vectors that were linearly independent within the set.
Exactly. So an example is the homework problem we just did. So let me just scroll up because I don't have to type it because we just did it. But now I could do it more formally. So what this says is that here are some vectors. Okay, they're not linear independent, but let's see if we can find a subset that is linear independent. And the answer is yes, we can. And here it is. First, third, and fifth. Do you see that I found it? So this was a kind of an important precursor to that theorem. So here we did it with an example, and the theorem says you can always do it. Any questions on that idea? Any questions? I do want to mention, and this is probably something you've never thought about, but I do want to mention it, is that we're in Rn, where n is a finite number. Are there any applications where you want to deal with infinite or infinity?
I'm sure there are.
I'm sure there's plenty, yeah.
Yeah,
But
there definitely are. And some of these theorems don't work in R infinity. Just let you know that. So the theorem we just stated does not work with R infinity because you're not going to be able to list a finite number of vectors because you have too many. Does that make sense? Any
that means
questions?
there's too many vectors for the too many vectors theorem.
You have an infinity vectors. Infinity is a hard thing to list. Does that make sense? So you're not going to be able to write down a list of linear independent vectors because there's an infinite number of them. Does that make sense? So that's just a note, is that everything we're doing, not in the class, but today, everything we're doing today is within Rn. Okay, do you think that's going to change on another day?
Yeah, most likely.
Absolutely, because we're going to have things like the set of all functions, and that's going to be a vector space, and it's going to be very badly infinite dimensional. You can't even list them with ... even, just let you know that. So I wanted to kind of make that remark because, I want to get you to get that in your head, because later on we're going to deal with things that are not Rn, things that are much higher. So any questions on this corollary? Again, the example doesn't prove it, but the example is an example of how it works and how you find it. How do you think you'd prove this in general? Thinking about the example. So here's a general proof idea. Any ideas? Okay, so I'm going to start out with when you have we have a subspace of Rn, there is this linearly independent vector such that the span is actually equal to V. So what are we going to do? We'll start with, so first thing is that start with V1. And just make it easy. I'll just not subscript it if it's okay for less typing. Okay. And when I say start with V1, that means just grab a vector. And I should say any non-zero vector, because zero vectors are never linear. You can never have that in a linear independent set. Okay, does that make sense so far? Can I do that? If you just have one vector that's non-zero, is it linear independent? What do you think?
Yes.
Yeah, because if a constant times that vector is 0, then the constant must be 0. Do you agree?
Yeah.
Yeah, that's all that is. Okay, then if all other vectors are in the span of V1, so in other words, they're all multiples of it, we're done. Do you agree? Because we just found a set such that the span of that set is the whole vector, say base, the whole subspace. Not pick a V2, not in the span of V1. Then V1 comma V2 is a linear independent set. Do you agree with that? Because if it's not, that was one of the theorems we had before. And then what do? We continue this process. Okay, so in other words, I'll just say it and then I'll write continue. Is that if V1, V2, if the span of that is our V, we're done. If not, find a V3. So continue. Okay, and then you have V1, V2, V3, do the same thing until you get V4. And you just keep going. This process cannot last forever. How come?
Because we have a finite number for Rn.
Yeah, in particular, it must stop after, or at least, or I guess by the nth step or earlier. Because any n plus 1 vectors that are, or any n vectors span that are linearly independent span Rn. Any questions on that? So that means that eventually we're done. And that's the whole proof. Any questions on that? So again, a lot of theory today. Some days are more theory, some days are applications. Today is definitely a theory day. Okay, that tells us the following, and this is really important. Here comes the next big definition of the quarter. Okay, and we're almost done for the whole quarter, by the way. There's a couple more, but most of them happen in this section. Okay, let V be a subspace of Rn. Then S equals V1 through Vk in V is a basis for V if 1, the span of S is equal to V, and 2, the vectors in S are linearly independent. Any questions on this definition? Any questions? Okay, let me give an example for you because it's really important, so we need examples. Let's consider, and I'm going to do row vectors because they're easier, right? Let's consider the plane z equals 2x minus y. First thing, do you agree that that plane is a subspace of R3?
Yes.
Yeah, given that you trusted me, certainly, do you all agree it goes to the origin? If you plug in 0, 0, 0, it works. And it's a plane, and I told you planes are good. Planes to the origin are good. Okay, then let's look at 1, 1, 1. Do y'all agree that's on the plane? And another vector. I guess I should make it look like a vector instead of a point. And let's get another one. How about 2, 0, 4? Is a basis for this plane. How do I show that? What two things do I have to show?
You have to show
That the
the
span
span
of
of them are equal, and that they're linear, and that the span is linearly independent.
Right. So not the span, but the S is linear independent. Okay. So first we got to show that the span of S is equal to V. So that means that if I have, let's write 1. If I have something on the plane, well, what does something on the plane look like? Well, it looks like an x, comma, y, comma, 2x minus y. And that needs to be equal to a times 1, 1, 1. plus b times 2 comma 0 comma 4. So for any x and y, I need to be able to find a b that works. Do you agree with that? An a and a b that work. Is that clear? So what can I do?
Set up a matrix.
Yeah.
Yeah, set the matrix, but I think before I set the matrix, because it's a little confusing what the matrix might be, I think I'm going to write down the system of equations, and that is a plus 2b. Wants to capitalize. A plus 2b is equal to x. And then we have a equals y, right? Because a plus b times 0 is y. And then we also have that a plus 4b is equal to 2x minus y. So for any x and y, I need to make sure that this works. Is that clear? So what I need now is, as you mentioned, I need to get a matrix out of this. And the idea here is everything's going to be beautiful. Okay, so how do I solve for a and b now? And make sure that this is always going to work.
RREF.
Yeah, let's make that matrix up. Okay, and here we need to write it as a matrix with the right-hand side also, because we have the x, y, and 2x minus y. So you have a, let's get the matrix. Always before that. There we go. So what do we have? We have a, which is, that's a 1a plus 2b is equal to x. We have 1 plus 0b is equal to y. And then we have 1a plus 4b equals 2x minus y. Any questions on that? Now we can start RREFing it. So what I can do is I can take row 1, multiply by -1, add it to row 2 and replace. That gives me a 0 there, a -2 there, and an x, negative x, or y minus x. It's the easier way of writing it. And then similarly, I can double row 1, multiply row 1 by -2 and add it. And I get a 0 there. And then I get a, make sure I did all this right. I think I might have made a mistake in here somewhere. A plus 2b is x. 2x minus y is 1. Hope that should work. And then what do I get for the next one? That should be a 0, right? And what about this guy? that one should be a negative y. I think there's an error there. Any questions on that? One, just a minute. 2, 0, 4, xy, 2x minus y. Any questions on that? xy, 2x minus y. And then what?
Find the pivot columns, right? Or
Yeah, this is why I'm worried. I think I made a mistake. So find my mistake. I hate when I make mistakes, especially offline. So we have 1, 1, 1, 2, 0, 4. Bottom left would be negative 1. So this guy right here. Let's see. Oh, yeah, because I only multiply by 1. Yeah, that changes everything. Yep, I knew I missed something. So I multiply by 1 and subtracting. That should be negative 2. There we go. And that should be a negative. That should be a x minus y. Much better. Any questions on that? And that should be positive 2. Yep. Okay, now look at row 2 and row 3. What do you notice about them? If I add them, what do I get?
0.
Yeah, if I add them, I get the 0 row, which is a good thing, by the way. I hate when I make a little mistake because it takes forever for me to find it. Okay, but I got it. So notice when you have this, from theory from the last chapter, what do we know about a solution? Is there a solution? And the answer is yes. Right? There's a solution because, and it's unique, because we have 2 pivots and the bottom is just 0 equals 0. There's no issue there. 2 variables, 2 pivots, and that's what we want. So what does that tell you?
tells us that there's a solution.
Yeah, it tells us it spans. Do you see? That's what solution means. So therefore, let me do the following so I can type less. Let's call it S. I like to call it S. S spans the plane. Any questions so far? All right, what else do I have to show?
Linear independency.
Yep, so I need to show linear dependence. So now what we need to do is we need to say, well, linear dependent means that if we have a constant times the first vector, always wants to capitalize, plus another constant, b times the second vector, and if that's equal to the 0 vector, that's what linear dependence means, we need to show that a and b are both 0. Any questions on that? So what I can do, and this is a nice little trick, is I can just use what I just did and just adjust the one little thing I need to adjust, which isn't much. And that is, I need to set it equal to 0, 0, 0, not xy, 2x minus y. And then that row stays all 0. In fact, I can even get rid of it if I want. I think I'll keep it in there just for fun. That column, I mean. It's always going to be 0, 0, 0 as a column. All right, the second, and then this -2 can be turned into a -1 by dividing by -2. It's one of our row ops. So that tells us that B is 0. And if B is 0, then A has to be 0. And by definition, these vectors are linearly independent. Any questions at all on that? Any questions? So therefore, we have a base, S as a basis for the plane. Any questions at all on this example? Okay, here's another example. I'm gonna let you read it because I forgot something and I want to make sure I don't mess up. All right, did you have trouble hearing me, by the way? I forgot my microphone. Now my microphone's plugged in. I don't know if that helps or not, but it should.
There was some cutouts, but otherwise it was pretty good.
Okay, yeah, that's what I found. The microphone makes it so there's no cutouts. Okay, so let's look at R4, for example. And as I mentioned, R4 is a subspace of itself. And if you let E1 be 1, 0, 0, 0, E2 be 0, 0, 1, 0, 0, 0, E3 be 0, 0, 1, 0, and E4 be 0, 0, 0, 1, we call this the standard basis. How do you know immediately that this is a basis?
Because it would be the identity matrix.
Yeah, because if I just pop this as a matrix as the identity, and that's as good as it gets, right? It's linear independent, spans, got everything, okay? So there's no problem with being a basis, but this is the definition of standard basis. It means that you have all zeros and only a single one in order, got it? And I'm gonna be using this a lot because that's how you learn in 6th grade how to graph a line, right? Or anything, is you think about the X coordinate and the Y coordinate. And that here we have the, W, X, Y, and Z coordinates, I guess, because there's 4 coordinates, but same idea. Any questions on that? All right, so there's, again, not too much to say about it other than we're gonna be using a lot because it's easy. I hope you all agree that was easy. Okay, then comes a theorem. It's called the exchange theorem. And here's what it says. Let's suppose that you have a set S equal V1, V2 through VR, and suppose it's linear independent in Rn. And let's suppose that each of the V's are contained in the span of this other set W1 through Ws. Then S has to be at least as big as R. Any questions on that idea? Okay, so it's kind of the too many vectors theorem, is that if you have too many vectors, you're going to be linearly dependent. Kind of works that way. And that's what this is that if you have more vectors, so if you had more vectors than this, if you didn't have enough vectors, then you're not going to make it. Any questions on this exchange theorem? We'll use it once in a while. Again, it's not as important as some of these other things, but it happens. Okay, what we're going to use more is this corollary. And that is if S and T are bases for a vector space V, or subspace V, then S and T contain the same number of vectors. So again, the reason for that is if they're both bases, Okay, then they're both linearly independent, right? So that would mean that S is greater than or equal to R, but also you can switch them and say R is greater than or equal to S. Any questions on that? So in other words, that if we have bases, you get the same number of vectors. And that is a very important theorem or corollary because it means that we can make a definition. And this definition we'll be using all the time. And it's easy enough that you won't have any trouble with it. It's not one people have trouble with. And that is the number of vectors in a basis for V is called the dimension of V. So you're used to this. You know what it means to live in a three-dimensional space. You know what it means that a paper is 2 dimensions. Hopefully you know that, right? And a line is how many dimensions?
1.
1.
2, isn't it? Oh, wait, no. Yeah, it's 1. I'm sorry.
A line is definitely 1-dimensional. And all you need is one vector in a line, and then multiples of vector will give you the whole line, right?
I was thinking of directional for some reason.
Yeah, definitely not. Direction's not important in this class, by the way. There's going to be no left and right. What's more important is dimension. Okay. Whereas a plane, you're not going to get a plane. You're not going to be able to get a plane without 2 vectors. Do you agree with that? Just kind of pictorially. And similarly, you're not going to get into the whole universe that we can see without 3 vectors. You're going to need an X, Y, and a Z direction. And are there different choices for the X, Y, and Z directions?
Yeah.
Absolutely. Could you double the length of your X direction vector, and do you still have a basis?
Yes.
Yeah, that's not a problem at all either. So there's lots of choices in getting a basis for a space like R3. But in all the choices, they're all going to have 3 vectors. You're never going to have 2 vectors to get a basis for R3. Is that clear? And similarly, if you're a plane, and that is something that we'll call that isomorphic to R2, you're going to need 2 vectors. Is that clear? Okay, so this is called the dimension. Okay, now when we looked at vectors as columns of matrices, what was the dimension? Using different words now than the word dimension. We've talked about it already.
It was the number of vectors by the number of components of the vector.
I'm looking for a word that starts with P. Number of
pivots.
Yeah, it was the number of pivots. Do you remember that? So the number of pivots will give you the dimension. Right? And then we found a basis by taking the pivots, going back to the original vectors and listing them. Any questions on that? Okay, so that's just a note, is that it's not unique to find a basis, but it is unique to find a dimension. Okay, next theorem. Do you agree? A lot of theorems and definitions today? Kind of this class. Okay, let's suppose we have S equals V1 through Vk. And now this is a subset of Rn. Then, if S is linearly independent and K equals N, then S is a basis for R. Okay, so to show something the basis, you need linear independent and you need span. So this is the same thing as that if S is linear independent and K equals N, then S spans. Okay, number 2 is if S spans Rn, then K must be at least as big as N. Okay, so if you want to span the XYZ space, then it says you need at least 3 vectors to do that. That shouldn't be a big surprise, right? Because if you have only 2, you're going to get a plane and not all space. If you only have 1, you're going to get a line. You need 3 to get space.
Anyone lost on that idea? Okay, if S spans Rn and K is n, then S is a basis for Rn. So notice 1 and 2 are important. 1 and 2 say that if you're trying to find a basis for Rn and you count the vectors and you have the right number, you have n, then you don't need to prove both linear independence and span. You prove whatever's easiest. Any questions on that idea? Any questions? Why is this true? Okay, so we're saying that if you have n vectors and it's linear independent, then it must span also. Because
Yeah, by definition.
yeah, because if it doesn't span, then by definition, we can find another vector that's not in the span, right? That's what it means to not span. Just add that along, and guess what? Now you have a set of linear independence vectors, and your set's bigger than n, and we already know that can't happen because the dimension of Rn is n, period. So that's number 1. Okay, so again, I can't write all these down because I don't have time, but hopefully I can say them. And if there's any questions on what I'm saying, I might be talking fast, then please stop me and I'll help you out. Okay, if on the other hand, if we span Rn and we have the right number of vectors, then we need to prove that they're linearly independent. Okay, well, if they're not linearly independent, then guess what? You can write one as a linear combination of the others, right? And that one that you wrote as a linear combination of the others, you can say, I don't like you, so I'm kicking you out, but you get the same spanning set, right? Any questions on that? But that's a problem because you can't have fewer than n vectors and span Rn. So we can't kick anyone out, which means they must have been linear independent. Any questions on the vocal proof for number 3? By the way, if you wait long enough, how can you find it in writing? Although it won't be perfect.
Going onto the syllabus and then checking the lecture notes.
How can you find exactly what I said in writing?
Oh, checking the Zoom transcript.
Yeah, exactly. You can check the Zoom transcript or go to YouTube and hit closed caption. Because I'm actually saying the proof. So it is a proof, whether it's just a spoken proof, but it's the same thing. Any questions on the theorem? I did 1 and 3. I'll let you think about 2. 1 and 3 are the biggies, by the way. That's what we're going to be using all the time. So what it says is that if you have the right number of vectors, then you don't have to show both linear independence and span. And it's usually easier to count the vectors than it is to show either linear independent or span. Counting is simple. Okay, and notice, by the way, Rn, not R infinity. None of this works with R infinity. You got all kinds of problems. So that's not today. Okay, next theorem. Again, today, theorem after theorem after theorem. But I don't want to miss any of these big theorems from the book. And that is, if V is a subspace of Rn, then there exists a basis for V with the dimension of V less than or equal to n. Okay, why is that true? Okay, this time I think I'll type it out. It's good, like every other, I think it's good to do some proofs. So let V be a subspace of Rn. Then if V is a basis, we're done. Sorry, then if what's the dimension of V is, so we have V as a subspace. Okay, then there exists a basis for V with the dimension less than or equal to n. So what we need to do is we need to find a basis. But we've already, can you find a basis? Does a basis always exist?
Yes, it always exists.
Yes, it always exists, because we know that a spanning set, so what we're going to do is we're going to start out with a spanning set for V. Okay, and that always exists. We did that last time. Do you remember that? You can always find a span. Okay. And then what are you going to do?
RREF the span and then find the pivots. Then
Yeah. So then form the matrix and RREF it. How many pivots can there be?
at most the amount of n.
There can be at most n pivots. Because remember that, yeah, we might have 100, let's say you might have, 100 different vectors in the span. So there'd be 100 columns, but there's at most n, and that might be, say, 5 rows. And when you REF, you can never get more pivots than the number of rows. That's what that is. Okay. Then the vectors that are pivot columns are a basis. Okay, because we have the right number of them, and it also has to be less than or equal to n. Any questions on the proof there? Okay, more theorems just for fun, because that's what this section is, or this part of this section. Okay, let S be the span of a bunch of vectors in Rn. Then there exists a subset of S that is a basis for S. Okay. So the nice thing is that's easy. That's immediate from the last one. How come? So proof, we basically already did it. Okay, well, think about it. So we have a span of a bunch of vectors, then there exists a subset that's a basis. Well, S is a subspace of Rn. Okay, the span is always a subspace. We showed that last time. Okay, last time meaning Friday. Therefore, this is true by the prior theorem. Any questions on that? Because it means that we can find a basis for it. And guess what? That's it. Okay. But now how do you know that it has to be one of these? Well, it has to be one of these by the proof of the final theorem. So maybe I'll write that down. Because in the proof, what we did is we grabbed our vectors, put them in a matrix, and then said, just take the pivots. And guess what? Those are those vectors. We're not having to change the vectors at all. Any questions on that? All right, we're getting there. We have a few more proofs left, theorems left, and definition, and we have 5 minutes. So I think we'll make it. Okay, so the next theorem. Let's suppose we have two subspaces of Rn, V and W. And let's suppose that W is a subset of V. Okay, usually puts a little equality on it, saying that you actually could have it to be equal to V. Then the dimension of W is less than or equal to the dimension of V. And if the dimensions are equal, then W equals V. Okay, why must that be true? Who can tell me why?
If dim of W is, if the dimensions of W are equal to V, and W is a subspace, then that means that, you know, they're equal. I don't know. It's a subspace that contains everything inside of it. I don't know how to say what I'm saying.
All right, you're missing the key word. So consider a basis for W. Okay, well, notice that a basis for W is a linear independent set in V also because W is in V. Is that clear? Any questions on that? So if you just consider a basis for W, then if, so, and that number of vectors in a basis is the dimension. Okay, so if they're, so if this, if, let's think about this. So if W is in V, so if W is not equal to V, take a vector in V that is not in W and add it to the basis. Well, how many, now we have more vectors. Do you agree? We have more vectors than we started with because we just added one. This is a linear independent set. So the dimension of W must be less than the dimension of V. Any questions so far? Okay. If W, let's see, sorry, is not equal to is what I want. So if W is not equal to V, that means that there's more vectors in V we can grab. Any questions on that? Okay, well, if the dimensions are equal, then the basis for W must also be a basis for V, because the basis for W is a linearly independent set of vectors in V, and we have the right numbers of them, and that's what we want. Okay, but then V is a span of those vectors. So W equals V, because W is also a span of those vectors. So that's the proof. And we have just a minute or two left, so I'm not going to prove these last ones. I'm just going to state it. So if V and W are subspaces of Rn with W and V, then a basis for W can be extended to a basis for V by adding a finite collection to the basis for W. Okay, we've kind of been talking about this the whole time. So in other words, if W is in V and W and they're both subspaces, then you can just say, well, if they're not the same, then grab something that's not in it, add it in there, and just keep going, and you won't be doing it forever because the most you can have is n. That's all that is. So I've kind of proven this theorem already. Okay. And then finally, a big definition which we've actually already gave you an example of, is the kernel of a matrix. So if A is a matrix, then the set of all V's such that AV equals the 0 vector is called the kernel of A. Do you remember me talking about that today? Without using the word kernel? Which I forgot to make it red because it's a definition. Let me scroll a lot. Show you the example. This is a long time ago. Was it that one? There we go. So here we go. Let A be this matrix. I looked at all the vectors V such that AV equals 0. Okay. I proved that that was a subspace. To find the kernel, you just RREF and then see what you get. In this case, the kernel actually is just a 0 vector. Because if you RREF, you'll get the identity. Because the determinant is 10, non-zero. But sometimes you get a kernel that's actually interesting. And we've dealt with it before. We just didn't have the word kernel before. So we're out of time. So let me stop the share. And let me stop the recording. And Wednesday we'll do more of this.